Good day everyone and welcome.
Today we delve into the fascinating world of large language models with our presentation titled CODEGEN2, Lessons for Training LLMs on Programming and Natural Languages.
We'll explore the challenges and breakthroughs in training these models, the cost implications, and our unique approach to unifying architecture and objectives.
Stay tuned for some intriguing insights and lessons from our research. Let's get started.
Large language models, or LLMs, have shown impressive performance across a variety of tasks, including programming languages.
This success has been leveraged in previous works, transferring these findings to programming languages and significantly reducing costs.
However, despite their merits, LLMs present several challenges.
The complexity of self-attention circuits, the unification of tasks, and the high costs associated with training these models are all significant hurdles.
Furthermore, the choices of model architecture, learning algorithm, and data distributions can lead to high monetary costs.
Our paper proposes a method to address these challenges. We aim to unify across architecture, objectives, sampling procedures, and data distributions. This involves forming hypotheses for each aspect and distilling our findings into lessons. This approach allows us to navigate the complexities and costs associated with LLMs, providing valuable insights for future research and practice. Diving into the key findings of our research, we discovered several important insights. Firstly, the prefix-LM architecture did not bring about any measurable improvements in our set of tasks.
Secondly, we found that infill sampling training is not without its costs.
Thirdly, a simple combination of causal language modeling and span corruption limited to within-file spans proved to be sufficient for our purposes. Fourthly, we observed that a mixture distribution of programming and natural languages holds promise for future developments. Lastly, we found strong evidence supporting the effectiveness of multi-epoch training, as demonstrated with our CODEGEN 2.5 model.
These findings provide valuable insights for practitioners and researchers in the field.
As we delve into our study, let's first take a look at the results on Lambda and PIQA for natural language and human evil for programming language over the number of training steps as shown in the figure on the right. This graph provides a visual representation of our model's performance across different tasks and stages of training.
Now let's discuss the motivation behind our research.
Large language models, or LLMs, have demonstrated impressive performance across a variety of tasks. Their simplicity, universality, and scalability make them a powerful tool in the field of AI.
However, they are not without their challenges.
The complexity of the self-attention circuit, the need for task unification, and the high cost of training are all significant hurdles we aim to address in our study. Our goal is to make the training of LLMs more efficient while maintaining or even improving their performance.
We believe that by unifying learning methods and model architectures, we can achieve this.
Stay with us as we explore this further. In our research, we tackle a specific problem: the complexity of self-attention circuits, the lack of unification in synthesis and understanding tasks, and the high cost of training multiple models. These challenges are significant because the choice of model architecture, learning algorithm, and data distributions can induce high costs. Therefore, unifying these aspects is crucial to make the training of large language models more efficient. Previous attempts to solve this problem have transferred findings from large language models in natural languages to programming languages. These models rely on self-attention circuits and can handle a variety of tasks, which reduces costs.
However, they also present unresolved challenges that we aim to address in our work.
The limitations of previous solutions are evident in the challenges we face. The self-attention circuit, for instance, forces us to choose between bidirectional or unidirectional representations. Furthermore, synthesis and understanding tasks remain separate, and the costs of training multiple models are significant. Our proposed approach aims to address these issues. We suggest a unification across architecture, objectives, sampling procedures, and data distributions. We formed hypotheses for each aspect and distilled our findings into valuable lessons.
The novelty of our approach lies in its attempt to address these challenges.
By unifying architecture, objectives, sampling procedures, and data distributions, we aim to streamline the process. We formed hypotheses and distilled our findings into lessons, providing a roadmap for future research in this area. In our research, we sought to unify various aspects of large language model training, including architecture, objectives, sampling procedures, and data distributions. This was an ambitious departure from previous methods, which lacked such comprehensive unification. We formed and tested hypotheses for each aspect, distilling our findings into valuable lessons. Our model was trained on a unique mixture of programming and natural languages, a novel approach that leverages the strengths of both modalities. We hypothesized that this could improve large language model performance on natural language tasks.
To test this, we trained a causal decoder on this language mixture. Furthermore, we introduced a new approach of multimodal data mixing, training our model on mixed data types.
This innovative method opens up new possibilities for future research in the field. Diving into the technical details of our research, we found that a simple mixture of causal language modeling and span corruption is sufficient.
This not only simplifies the training process, but also reduces model complexity, making it more efficient. Next, we explored the potential of data mixing.
Our findings suggest that a mixture distribution of programming and natural languages holds promise. This could be a game changer, potentially improving the performance of large language models.
Lastly, we discovered strong evidence for the effectiveness of multi-epoch training, particularly with our CODEGEN 2.5 model. This could significantly impact future training of large language models, making them more effective and efficient.
These findings provide valuable insights into the training of large language models and open up exciting avenues for future research. Our technical results have shed light on several key aspects of large language model training. Firstly, we found that the prefix-LM architecture did not bring about any measurable improvements on our tasks.
This suggests that the architecture may not be as influential in LLM performance as previously thought. Secondly, we discovered that infill sampling is not as cost-effective or efficient as we initially anticipated. This indicates a need for alternative approaches in this area.
Thirdly, we found that a simple mixture of causal language modeling and span corruption was sufficient for strong performance. This implies that complex methods may not always be necessary to achieve good results. Lastly, we observed that a mixture distribution of programming and natural languages showed promise. This suggests that integrating different language data can enhance a model's versatility and performance. These findings provide valuable insights for future research in the field of large language model training.
Our technical results highlight the effectiveness of multi-epoch training.
We found strong evidence that extended training can significantly improve performance. This is a key takeaway for practitioners looking to optimize their models. In our ablation studies, we examined the prefix-LM architecture.
Interestingly, we didn't observe any measurable improvements.
This suggests that other aspects of the model may have a more significant influence on performance. We also explored infill sampling. Our findings indicate a need for further exploration of other sampling methods to make training more efficient. This is an area ripe for future research.
Finally, we looked at a simple mixture of causal language modeling and span corruption. Our results indicate that this simple approach is sufficient, suggesting that more complex methods may not necessarily yield better results.
This could simplify model design and training, making it more accessible for practitioners. In our research, we tackled the high cost and complexity of training large language models, or LLMs, by attempting to unify various aspects such as architecture, objectives, sampling procedures, and data distributions. We formed hypotheses for each of these aspects and distilled our findings into valuable lessons.
Our evaluation of the model was conducted in a zero-shot manner on a variety of tasks, both in programming and natural languages.
We believe our findings will be beneficial to the community, and to facilitate further research, we will be open sourcing the training implementation and the resulting family of CODEGEN2 models. This will provide a valuable resource for future exploration and development in this field.